I'm Seema and welcome to part 17 of the chapter Alcohols, Phenols and Ethers. In the previous video, we were talking about the acidity of alcohols. In this video, I'll explain the acidity of phenols to you. We already know that according to the Lowry-Bronsted concept, anything that releases H-positive ions or hydrogen ions in a chemical reaction is said to be an acid or is an acid. And anything that releases OH negative ions in a reaction would be a base. So by definition, anything that gives out H positive ions should act as an acid. And we see here in these two reactions that when phenol reacts with sodium, it releases sodium phenoxide and hydrogen. So it liberates hydrogen. So anything that liberates hydrogen when it reacts with metals, resulting in the formation of this ionic part, that is the sodium phenoxide. Here oxygen is negatively charged and sodium is positively charged. The hydrogens which are released as H positive gain those two electrons that neutral sodium loses and has to form neutral hydrogen. In other words, in this reaction, phenol liberated hydrogen as H positive, therefore it is an acid. Similarly, when phenols react with sodium hydroxide also, they release water and sodium phenoxide is formed. And this water again would be formed because sodium hydroxide is Na is positive here and OH is negative. So hydrogen should be liberated as H positive so that Na positive takes its place in the molecule. So both these reactions show the acidic nature of phenols. Now let us understand this acidic nature of phenols. In the case of alcohols, the OH, that is the OH group, the hydroxyl group, was attached to a carbon that was sp3 hybridized. If you remember, the general formula of an alcohol is ROH, where R stands for a methyl group, any alkyl group. It could be primary, it could be secondary, whatever. But it is usually an alkyl group. So in an alkyl group, the carbon is sp3 hybridized. The difference here in the case of phenols is that the carbon to which OH is attached is sp2 hybridized. Do you see? In the benzene ring, each carbon in the benzene ring is sp2 hybridized. So the difference here from alcohols in phenols is that the OH in phenols is attached to a sp2 carbon. So what is the characteristic of an sp2 carbon? An sp2 carbon forms smaller bonds. Therefore, it is more electronegative in a way. Because the bond is shorter, it has a greater tendency to pull the electrons towards itself. Other than that, a benzene ring shows delocalization. Since it shows delocalization, it can pull electrons and it can cause resonance. Those electrons can be moved around in the benzene ring, which provides extra stability to the benzene ring where the charge has been separated, right? Because resonance leads to more stability. So we find, therefore, benzene has a tendency to pull the electrons towards itself. Therefore, benzene is an electron withdrawing group. It withdraws electrons. So we see that OH, number one, in phenol is attached to an sp2 carbon, which forms a shorter bond. So the chances of the electrons moving is more. And secondly, that the benzene ring is an electron withdrawing group, which makes the OH more polar. How does it make the OH more polar? Since the electrons are being pulled down here, if you see in this resonance, in these structures, the resonance structures of phenol, this is phenol. The oxygen has these lone pairs of electrons which are attracted by the sp2 carbon of the benzene ring, and it can be delocalized in the benzene ring. Therefore, this double bond, the pi electrons of this double bond are pushed to the next site, the next location, the next carbon, while this carbon pulls this lone pair of electrons to form a double bond. So when the pair of electrons moves from oxygen to form a double bond, oxygen itself acquires a positive charge, right? And the negative charge now is at this ortho position. Do you see? As soon as the negative charge comes on the ortho position, what happens? The negative charge tries to form a bond. It tries to form a pi bond. When it forms a pi bond adjacent to it, the pi electrons present here on this carbon, they are pushed to the next carbon. Since they are pushed to the next carbon, we find that this electron forms the bond here, but the pi electrons of this bond were pushed and the negative charge now is at the para position. Again, the negative charge is not stable, so it tries to form a pi bond adjacent to it. So it moves further and it tries to form a double bond here. But the pi electrons of this double bond are now pushed because too many electrons, when they come close, repulsion occurs. So these electrons will repel the electrons of the pi bond, and therefore the electrons of the pi bond will be pushed and you get the negative charge on the next carbon, while this negative charge will now form a pi bond here. Right? So what do we see? We see that in these on the next step, what happens? This negative charge tries to form a bond here but pushes the double bond, the pi electrons of this double bond, back to oxygen. So the electrons go back to oxygen, this returns to a single bond and a pi bond is formed here, and you get back the kind of the original structure, but only this time the pi bonds are at different positions. If you look at the molecule in the same direction, the pi bonds were between 1 and 2, now they are between 5 and 6. So although if you look at it from behind, it is the same molecule, but basically you know that the pi bonds have kind of moved around the entire molecule. So this is called resonance, which imparts stability. That is one thing. Second, did you notice that it caused a charge separation, positive and negative? So a polarity is created in the molecule itself. Besides this, a polarity is created between oxygen and hydrogen also. When oxygen becomes positively charged, it means oxygen is now deficient in electrons. And oxygen is a more electronegative element than hydrogen. Hydrogen has a tendency to lose electrons. It is more like, it has more characters like metals. It tries to lose that one electron and form H positive. So what happens? Oxygen has a stronger tendency to pull electrons towards itself. The benzene ring is even stronger in pulling electrons, so it pulls a pair of one electron, actually not a pair, one still remains with oxygen, but it pulls an electron which starts revolving or which starts resonating inside the benzene ring. Therefore that electron is no longer available. So this oxygen, which has a stronger tendency to pull electrons but is positive, it is deficient in electrons, pulls the electron from hydrogen as soon as it gets a chance. So in a chemical reaction, this oxygen will have a tendency to pull away the electron from hydrogen, and hydrogen will be liberated as H positive. And the moment hydrogen is liberated as H positive, the phenol molecule is acting as an acid. Right? So this is basically what is happening in why phenols act as acids. So I'll repeat it now. The OH in phenol is attached to an sp2 carbon, which is more electronegative. And the benzene ring is an electron withdrawing group. Therefore, it pulls the electrons towards itself, making OH more polar. Not only is it making the whole molecule polar, it is making the O and H bond also more polar. Because oxygen is deficient, it needs electrons more, and hydrogen can easily liberate that electron. So it is kind of helping the hydrogen. It's making it easier for hydrogen to lose its electron and leave. So the reaction of phenol with sodium hydroxide shows that it is a stronger acid than alcohols and water. When I was discussing alcohols in the previous video, if you do not remember it, I would encourage you to move back and watch that video. But otherwise, let me just briefly explain it to you again. When the hydrogen is liberated, you get, in the case of alcohols, you get an alkoxide ion. And in the case of phenols, you get a phenoxide ion, right? In alcohols, what did we do? We took the alkoxide ion and we made it react with water. So alkoxide ion was present and HOH is water. What happens when we make it react with water was that water liberates the H positive and forms ROH, and OH negative is left behind. In other words, in this reaction of RO negative and H2O, H2O acted as the proton donor. It donated H positive, and anything that liberates H positive is an acid. And in this reaction, RO negative accepted that proton. It means that it acted as a base. So in comparison to water, the alkoxide ion acted as a base, which shows that alcohols are weaker acids than water. If you compare the acidic strength, water is a stronger acid because when you took the alkoxide ion, it was water who liberated. If the alcohol was a stronger acid, then the alkoxide ion would have been more stable, and when you made it react with water, water would not have liberated the hydrogen ion, and alkoxide ion would have remained as alkoxide ion, which does not happen. So from this reaction we concluded that alcohols their acidity is so low that they are even less acidic than water. And if we now try to understand this statement again, that reaction of phenol with NaOH shows that it is a stronger acid than alcohols and water. How would you know that it is a stronger acid than alcohols and water? Make it react with sodium hydroxide. You will get the phenoxide ion, that is sodium phenoxide. If we take this phenoxide ion and make it react with either alcohol or water, we notice that neither alcohol nor water can liberate the H positive ion to give you back the phenol. They do not give the H positive ion to give you back the phenol, which means that phenol is actually a stronger acid than both alcohols and water. Okay? Moving ahead with this explanation, due to higher electronegativity of sp2 carbon, since this sp2 carbon is more electronegative of the phenol, AROH is phenol, the electron density on oxygen decreases. This you saw, the electron density on oxygen decreased. One pair of electrons was used to make a second bond. So the one electron lost one electron because this pair of electrons was belonging only to oxygen, but when it forms a double bond here, it forms a pi bond here, one electron belongs to oxygen and the other electron is now being used up by the next carbon. So it loses electron. So we say that electron density on oxygen decreases because sp2 carbon is more electronegative. So as it is, the presence of an sp2 carbon pulls the electrons towards itself, and the benzene ring helps in that because the benzene ring is ready to pull that electron, suck it in and make it participate in resonance. So we say due to higher electronegativity of sp2 carbon of phenols, the electron density on oxygen decreases. This increases the polarity of the OH bond. You remember how I explained this to you? It increases the polarity. Not only the molecule becomes polar, but this bond also becomes polar because now oxygen is deficient. It is in electrons and it is the more electronegative element. So it has a stronger need to pull the electron from hydrogen, which as it is willing to give its electron. So it tries to pull the electron from hydrogen. So here oxygen kind of becomes more electronegative. It is electronegative, and that electronegativity, that deficiency increases, and hydrogen becomes more electropositive, or it has a better chance to lose its electron. So the OH bond, this increases the polarity of the OH bond, and an increase in the ionization of phenols than in alcohols. The ionization, that is loss of hydrogen as H positive, is more in the case of phenols than in alcohols because of both of these factors, the sp2 carbon and the electron withdrawing nature and resonance of the benzene ring. If you compare the stabilities of the alkoxide ion, that is, this ion is alkoxide ion, and the phenoxide ion, if we wanted to compare these two ions, which do you think will be more stable? the phenoxide ion is more stable, which we noticed when we made it react with alcohol and water. It did not react with alcohol and water to take the hydrogen ion from either alcohol or water, which proved one thing, that phenol is more acidic, but it also shows that the phenoxide ion is more stable. But in the case of alkoxide ion, when you made it react with water, it took the hydrogen from water, showing that this is less stable than even water. So how do we understand, again, how do we explain the stability of phenoxide ion? The same thing. In the case of alkoxide ion, the negative charge on oxygen is only on oxygen. It is localized, it is fixed in one place. But in the phenoxide ion, again, due to the benzene ring, due to the electron withdrawing nature of the benzene ring, this negative charge would distribute or move around in the benzene ring in resonance. And therefore also the phenoxide ion, wherever there is resonance, there is more stability. Resonance imparts stability to the species. So we say, if we are comparing the stabilities of alkoxide ion and the phenoxide ions, in alkoxide ion, the negative charge on oxygen is localized. It does not move. But in phenoxide ion, it is delocalized. Sorry, I've written pH. It should be AR. Oh, negative. In the case of phenoxide ion, it is delocalized, which makes it stabler and favors ionization of the phenol, AROH. It favors the ionization because the phenoxide ion, which is produced as a result of liberation of H positive ion, makes the phenoxide ion more stable due to resonance. So in phenol also, if you notice, delocalization was present. Now the question is, here also delocalization is there, here also the negative charge is revolving, then how is this more stable than this? Why do we say that the phenoxide ion is more stable? Why would the reaction take place? The resonance was already taking place here. Why did it liberate the hydrogen at all? For that, I've already explained to you the points that hydrogen, this bond also becomes more polar, thus facilitating the loss of hydrogen. But phenoxide ion will be more stable than the phenol. Why? Because in this case, there is a charge distribution. You have both positive and negative charges. Since you have both positive and negative charges in this makes it less stable than the phenoxide ion. So it becomes less stable than the phenoxide ion because both the separation of charges is there, and the separation of charges is also created as a result between O and H. So the phenol is less stable than the phenoxide ion, and that is why the reaction takes place where the formation of the phenoxide ion is favored. So in phenol also delocalization is there, but there is a charge separation that makes it less stable than the phenoxide ion. And the phenoxide ion does not have that, when there is a charge separation, you have a pull on both sides, positive charge, negative charge, the pulls are opposite. But in this case, it is only the negative charge which is revolving, thereby making it more stable. Now, if you remember when we talked about alcohols, I told you that if the alcohol is a primary alcohol, it is more acidic. But a secondary and a tertiary alcohol, as the number of alkyl groups keeps on increasing, which is attached to that, the carbon which is attached to the alcoholic group or the OH group, if that group is, if it is a primary alcohol, it is a methyl group, ethyl group, whatever. If it is secondary, it has another carbon attached to it. If it is tertiary, it will have 3 carbons, other carbons attached to it. So as the number of methyl or alkyl groups keeps on increasing, alkyl groups are electron donating. As it is, what did we notice here in the case of phenol? What made phenol more reactive or more acidic? An electron withdrawing group. That the benzene ring is electron withdrawing, which increases the polarity of OH bond. But alkyl groups, they are electron donating groups. So they kind of increase the density of electrons on oxygen. And oxygen does not, since it has its electrons and it gets even more electrons being pushed towards itself by the alkyl groups. If it is primary, just one alkyl group, secondary, two alkyl groups, tertiary, three alkyl groups, the polarity between the OH bond keeps on decreasing with increasing alkyl groups. So as the number of alkyl groups increases, the acidity of phenols decreases, because now oxygen does not need electrons. It is getting those electrons from the electron donating groups, or they repel electrons, they push electrons towards oxygen. So the need of oxygen is not as strong as it is in the case of phenols. In phenols, the oxygen becomes positively charged and the need of electrons in the case of oxygen increases, which makes it easier for hydrogen to leave. It increases the polarity of the bond. That does not happen in alcohols. So looking at this, if we had substituted phenols, if this is phenol and we had it substituted, the phenol had substitutions, how would it affect the acidity of the phenol? The electron withdrawing nature of benzene ring makes it more acidic. So any group which will withdraw the electrons more towards the benzene ring will make the phenol more acidic. Logically, you can understand that. So if there is a group which is pulling electrons towards the benzene ring, thereby making the oxygen even more electron deficient, it will make the phenol more acidic. So in substituted phenols, the presence of electron withdrawing group, for example, nitro group is an electron withdrawing group, it enhances the acidic strength of phenol. But if you have an electron donating group like methyl group, like alkyl group, that will reduce the acidity of phenols as it did in the case of alcohols. Now, in this case, not only electron withdrawing or electron donating groups, the position of these groups will also determine, the position of these groups will also determine whether the acidic strength is increasing or decreasing, right? But this I will explain in the next video, where we'll also be taking examples, and we'll be doing example 11, solved example 11.4. So we'll do that video tomorrow. I'll explain that better. I'll just read this out now and explain this in more detail, because that will make it clearer to you about the acidic strength. So in substituted phenols, the presence of electron withdrawing group, for example nitro group, enhances the acidic strength of phenol more at the ortho and para positions. This is if they are present at ortho or para positions. The electron withdrawing group will, if it is present at ortho and para position, it will enhance the acidity, because the negative charge, wherever it is present, if you have the negative charge, the negative charge is present at the ortho and para positions, if you see. Since the negative charge is present at the ortho and para positions, the negative charge, that is the electrons, negative charge is nothing but electrons. If you have an electron withdrawing group here, it will have a stronger tendency to pull the negative charge to the ortho and para position. That is why whenever you have an electron withdrawing group at the ortho or para position, it will help the movement of the electron towards the ortho and para position. But if you have the nitro group at the meta position, it will not help in the increasing the acidity of the phenol. Rather, it might create a hindrance. It will decrease the acidity of phenol. So I have done a few videos about the acidity of organic compounds by the Carrier method. I've done a series of videos on the acidic strength of organic acids. So I would suggest, since you're in the 12th grade, to really go through those videos. That will not only clarify your acidic strength of, your theoretical knowledge about the acidic strength of not just alcohols and phenols but all other classes of organic compounds too. So I feel that series would really help you. So please look for that playlist, and I'll try to put that playlist, a link of that playlist in the description box below, and click that and try to see that playlist. That'll really clarify a lot about the acidic strength of all organic compounds. But of course, as we do them, I'll be explaining it to you. But if you do that in one consolidated form, it'll really clarify your concepts about the acidic strength. So in the case of, if the electron withdrawing group is present at ortho and para positions, it'll enhance the negative charge on the phenoxide ion, and thus it'll increase the acidic strength of phenol. If you have electron releasing groups like methyl, they do not favor the formation of the phenoxide ion, and thus they result in the decrease in the acid strength. So cresols are less acidic than phenol. Now this last paragraph I will be taking up again in the next video, and I'll explain this better to you. So with this, I'll wind up today's video. If you found the video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.